Hello, welcome to this course Analog Circuits. Now we are in the week 8 of this course. So in the past week we had been discussing about multivibrators, that is the astable, bistable and the monostable multivibrators. Now we are going to start another topic on this general topic of nonlinear circuits, nonlinear analog circuits that is. So in this module we will be discussing about the Zener effect. Now the Zener effect is a very popular technique used for voltage regulation. So voltage regulation means you are given an input voltage and you do not want the output voltage to exceed certain value. So in those applications the Zener effect or the Zener diode as the device that is used, that is known, that comes in handy. So let us discuss about this Zener effect. First of all, we have to understand that the Zener effect is what is known as a quantum effect. Usually when a material, any material is subjected to high voltages, at a certain high voltage this will break down. Break down means the electrons, suppose this was an insulator initially, under the influence of the very high voltage the electrons will be pulled out and this material will go from a non-conducting to a conducting. Now usually when this happens the material cannot go back to its previous state. So if it breaks down, what we call an electrical breakdown, if there is an electrical breakdown then the material cannot come back to its initial state. However, this Zener effect, what happens is that due to the special construction of the diode, now we will not go into the details of the construction of the diode, just know that there are some special techniques used for constructing the Zener diode such that when a high voltage is applied there is a lot of charge carriers which are formed, but then once the high voltage is reduced or we go back to the initial state, the material also comes back to its initial state. So that is the Zener effect. That is different from the normal electrical breakdown phenomena that we know. So a Zener diode, this Zener effect is usually exhibited by a device called the Zener diode. The symbol for a Zener diode is like this. Okay. And the I versus V characteristics of a Zener diode is something like this, that is the current and voltage relationship is something like this. So just like the threshold voltage or the forward bias threshold voltage of a diode, we now have a reverse threshold voltage. If the voltage across the Zener diode is made more negative than this VZ0, then there will be a sudden spike in the current flowing through the diode, or the resistance offered by the diode in the reverse bias region will suddenly fall. And in fact we will fall and go to a value say RZ. So usually we know that in the reverse biased state a diode cannot conduct any current, but for this Zener diode when the voltage is more negative than VZ0, there will be a sudden spike in current and the resistance goes from a infinite value to some finite value R z. This R z, by the way, is a dynamic resistance. Dynamic resistance means that it is a AC resistance, that it responds only when there is an AC input. Now, the circuit that as I mentioned, the Zener diode, the most popular application of a Zener diode is for voltage regulation. So, let us draw the circuit for that voltage regulation. So, the circuit is very simple actually. You have a source Vs with an internal resistance R. This is our Zener diode, and this output voltage that is produced by this Zener diode is fed to some device. Now, the equivalent model of this Zener diode based on the characteristics that I just showed can be represented like this. So, there is an internal resistance AC resistance R z, and there is a voltage source V z 0 representing the threshold voltage. So, when the voltage becomes more negative than V z 0, there is a sudden spike in current flowing. Okay. By more negative, I mean between this terminal and this terminal. Okay. So, it is, please do not confuse it with the forward biased threshold voltage of a normal diode. When I say more negative than V z 0, because for example, if I give this circuit diagram, then it almost appears as if it has to be more positive than V z 0. No, note that a Zener diode always works in the reverse biased condition, and here I have connected this Zener diode in a way that when the source voltage increases, it becomes it goes into the reverse bias region, and the higher the source voltage is, the more deeper it will go into the reverse bias region. So, how to analyze this? Now, first of all, see that because this Zener diode has an internal resistance R z, and also the characteristics of a Zener diode are like this. So, it is not a perfect cutoff circuit, that is, if the voltage becomes more negative than V z 0, it is not that it will be immediately cut off the output, or there will be a huge surge in current that will short the output. No, it is not like that. Because of this finite resistance R z, a Zener diode is just like any other device, not an ideal cutoff device, and we have to analyze it properly. So, to analyze it, how do we do that? Let us look at this current IL. So, this current IL, if I keep it here, if I IL go down a bit, yeah, is given by this current that is the current from the source, and suppose the current through the Zener diode is I z, then I L will be equal to the difference of I and I z, right. Now, what is this current I? Can I write this as equal to V s minus V 0, okay, upon R, and what is this current I z? Can I write it as V 0 minus V z 0 upon small r z, okay. So, then simplifying I get this as equal to V s upon R if I okay, plus V z 0 upon R minus V 0 into 1 upon R plus 1 upon R z. Okay. So, further solving this I will get V 0 1 upon R plus 1 upon R z, okay, is equal to V s upon R plus V z 0 upon R minus of I L, okay. And from this I can write the formula for V 0 as equal to V s R z upon R plus R z plus V z 0 R upon R plus R z minus I L R z in parallel with R. Okay. So, what this equation basically means is that if see V 0 is a function of V s, and as V s varies, V 0 will also vary. Of course, it will depend on the other parameters of the circuits like this capital R and small r z, but it is not that if V s becomes very high, then V 0 will stay constant, or it is not a perfect cutoff like that. Now, two terms that are frequently used in the as a performance criteria of a Zener diode are, one is known as line regulation, which is defined as the change in V 0 due to change in the source voltage V s, and the other parameter that is also a performance parameter of a Zener diode is what is known as load regulation, which is the change in V 0 due to change in the load current. Now, this ratio is similar to a derivative, and if we go back to this equation for V 0, then change of V 0 with respect to change of V s is simply equal to R z upon capital R plus R z, because the other terms, once we differentiate both sides with respect to Vs, this term and this term will be 0, only this term which is a function of Vs will remain. And so, this delta V0 upon delta Vs can be written as Rz upon R plus Rz. Okay. Similarly, if we want to find out this delta V0 upon delta IL, then we go back to the equation for V0, differentiate both sides with respect to IL, then this term and this term will cancel or not exist after differentiation, only this term will exist, and the value of delta V0 upon delta IL will be equal to minus Rz parallel to R. Now, what do we see from these equations? By the way, why are these so important? Line regulation says that how much will V0 change due to change in Vs, because we ultimately want an ideal voltage regulator, right. So, ideally what we want is that the change in V0 should be 0 for any change in the supply voltage Vs. Similarly, we also want that the output voltage should be immune to any change in the load. If we change the load value, then our load current will also change, and this parameter is a measure of how stable our output voltage is with changes in load. So, this measures how stable our output is with respect to changes in the supply side, and this measures how stable our output voltage is with respect to changes in the load side. Now, from both these equations we see that if R is made very high, both line regulation and load regulation become very low, isn't it? If so, this I can write as equal to minus Rz R upon Rz plus R, and this is in turn equal to minus Rz upon Rz upon R plus 1. Usually this Rz value is a small value. So, if my R is very high, then this will reduce to minus Rz, and Rz being a very small value, our load regulation value will also be, the magnitude of the load regulation will be small. Similarly, the line regulation also, if R is made very high, then delta V0 upon delta Vs becomes negligible. So, that is the way to do it. If my R is made very high, then we can ensure that our line regulation and load regulation is very good. So, then is that the way to do it? That is, if we just make the value of R very high, can we ensure that that all our problems are solved? Not quite. Ideally, we could have made this R equal to infinity, but then there is also the problem that we have to maintain a minimum current flowing through the Zener diode. So, Zener diode for operation in reverse bias mode needs a minimum current flowing through it, and let us say I call this minimum current as Iz min. Okay. Now, coming back to the circuit once, suppose the current flowing through the IZ, okay, is equal to, or the current IZ flowing through the Zener diode is equal to the minimum value IZ min, then what is the current flowing through the load, this IL. Now, we know that IL is equal to current from the source minus the current through the Zener diode. Okay. Now, if this I is fixed, then the maximum load current that can be supplied is given by I minus IZ min, right. So, my load supply current is constant. If my supply current is constant, then and suppose the minimum current is flowing through the Zener diode, then the maximum current that I can supply to the load will be IL max, and that will be given like this. Now, I is given by what? The supply current is given by the source voltage minus the output voltage upon the internal resistance of the supply source. So, this in turn can be written as, so I have I equal to Vs minus V0 upon R, which in turn is equal to Vs minus Vz0 minus IZ min into Rz. So, where did I get this relationship? If I go back to my circuit, the voltage, output voltage V0 can be written as the total voltage from here to here, and that is equal to the diode drop Vz0 plus the voltage drop across this resistance Rz. So, that is, and since the current flowing through the diode now is Iz min, so we write, instead of Iz, I am writing Iz min, this whole expression upon R, and therefore, IL max can be written as Vs minus Vz0, okay, minus Iz min Rz upon R minus Iz min. This follows from this equation which I had written earlier, this equation. Okay. So, here I have just substituted in place of I this equation. So, from here the value of R that we get is equal to Vs minus Vz0 minus Iz min Rz whole upon IL max plus Iz min. Okay. Now, suppose there is a minimum value to this supply voltage also. So, then the value of R will be equal to V s min minus V z 0 minus I z min R z upon I L max plus I z min. So, if my now this value of R that I get is for the worst case. By worst case I mean when the supply voltage is at a very at its minimum value, okay, when the minimum current is flowing through the Zener diode, then what should be the maximum value of R? If R goes above this value that we just derived, then there is a possibility that the current flowing through the Zener diode, this current flowing through the Zener diode will fall below its minimum value required for the operation of this diode. And so, that is why R should not be higher than this value. So, ideally we wanted R to be equal to infinity, but R max, there is a certain maximum value of R given by this expression, above which we cannot go. If we go, then either then there is a possibility that the Zener diode will stop operation because of the current flowing through it being lesser than its minimum value. So, I hope I was able to convey this concept of Zener diode to you properly. It is, as I said, used mostly for voltage regulation. In the next module, we will be covering the topic of rectifiers. So, thank you.